Hello, everyone. Welcome back to another episode of Elemental Distress, the only show where we solve all of your elemental problems and questions. We wanted to thank everyone for the support on our last episode and your feedback on what element we should talk about this week. We tallied up all your votes, and the element of the week chosen by you guys is... I am titanium. That's right, titanium. But before we get into all the good details of our friend Titanium, we thought we should do a special segment on the history of the creation of the atomic model and the scientists who made it possible. And to make this even more special, we thought we should bring in some expert special guests to tell us more about some atomic history. Thanks for coming to the show, Angeli, Gabriella, and Jordan.
Thank you for having me. I thought we should start off at the beginning with our good old friend John Dalton. Dalton lived from 1766 to 1844. And made his contributions in about 1803. His theory was first in claiming that all matter is composed of atoms, while describing their properties. He also came up with 4 postulates. The first postulate is that all matter is made up of atoms. Atoms are indivisible and indestructible. They are solid, massy, hard, impenetrable, movable particles. He didn't have necessary instruments in order to determine if the atoms had internal structure. The second postulate is all about atoms of a given element are identical in mass and property. This idea still holds true to some extent. However, no 2 elements have the same exact set of properties. The third postulate is that compounds are formed by a combination of 2 or more different kinds of atoms. The fourth postulate is that a chemical reaction is a rearrangement of atoms. This theory was based on the law of conservation of mass and the law of constant composition. The law of conservation of mass says matter cannot be created or destroyed in a closed system, which holds true for any chemical reaction. The law of constant composition says a true compound will have the same proportion of all elements it contains.
Next scientist up on our list is J.J. Thomson. He made his contributions around 1897. Thomson discovered the electron by experimenting with cathode ray tubes. Through this cathode ray tube experiments and using negatively and positively charged particles, Thomson realized that the accepted model of an atom did not account for negatively or positively charged particles. He discovered that all atoms contain tiny negatively charged subatomic particles, or electrons, that are located inside something positively charged. He proposed the plum pudding model, which added negatively charged particles, raisins, into the positively charged space, dough. He failed to recognize that the positive charge was also particles. His findings were controversial at first, but were eventually accepted and adopted by scientists. Now on to Ernest Rutherford. He made his contributions around 1911. He was a former student of our friend J.J. Thomson. He proved the plum pudding model to be incorrect. He performed gold foil experiments with alpha particles. Rutherford aimed alpha particles at solid gold foil and recorded the location of the alpha particle strikes fluorescent screen as they passed through the foil. This showed that some particles did not pass through the foil but were deflected off at an angle. The gold foil experiment led Rutherford to conclude that the atom consisted of a small, dense, positively charged nucleus in the center of the atom, negatively charged electrons surrounding it. He is known for proposing the nuclear model of the atom. Next up is James Chadwick. Chadwick lived from 1891 to 1974 and made contributions in 1932. He was a member of the British MAUD committee. He is known for the discovery of the neutron in 1932. Neutron is a particle with no electric charge, which makes up part of a nucleus of an atom. Chadwick discovered that bombarding elements with neutrons can split the nuclei, generating a huge amount of energy. This led us to the discovery of nuclei fission and the creation of the atomic bomb. Chadwick discovered that bombarding elements with neutrons can split the nuclei, generating a huge amount of energy. This led to the discovery of the nuclei fission and the creation of the atomic bomb. This concluded that nuclear weapons were not impossible to make. Now on to Francis William Aston. He was a British physicist who won the Nobel Prize for Chemistry in 1922. He discovered isotopes by using a mass spectrometer and for formulating the whole number rule. that isotopes have masses that are integer values of the mass of the hydrogen atom. The mass spectrometer is a device that separates atoms or molecular fragments of different mass and measures those masses with great accuracy. An isotope is two or more forms of the same element that contains equal number of protons but different number of neutrons in their nuclei, and hence differ in relative atomic mass but not in chemical properties. Aston is most known for discovering the 212th of the 287 naturally occurring isotopes, which he won a Nobel Prize for. Now time for Niels Bohr. He found that electrons should move around the nucleus, but only in prescribed orbits, when jumping from one orbit to another with low energy. A light quantum is emitted. Bohr's theory could explain why atoms emitted light in fixed wavelengths. Getting towards the end, it is now on to Werner Heisenberg. He lived from 1901 to 1976 and made contributions in 1924. He formulated quantum mechanics using matrices. He is known for the uncertainty principle and the theory of quantum mechanics. The uncertainty principle is that we can never know for certain where a subatomic particle is. This is because every particle moves in a wave-like behavior. Therefore, it is likely it will be in the location, but not certain. The quantum theory says the mechanical quantities like velocity and position be represented by matrices and not numbers. A quantum mechanical particle cannot continuously radiate radiation. It can only emit photons. The particle starts in orbit number n, emits a photon, and ends up in orbit number m.
Wow, the atomic model has come a long way. Are there any other scientists?
Finally, our good friend Einstein. He is known for the quantum theory. This says that energy exists as discrete packets, which are called quantums. This allows scientists to be able to describe the interaction between energy and matter down through the subatomic realm. Einstein wanted to describe nature on an atomic level, rather than use it for physics. Bohr and Planck also contributed to this theory, each receiving Nobel Prizes. He also contributed to the photoelectric effect. This effect was only realized due to his work on quantum theory. He described the light as quanta and won 1921 Nobel Prize. He proposed that light didn't behave like wave, but like a particle, known as the photon. The photoelectric phenomenon is that the energy of the electrons don't depend on the intensity of the light. Each electron can only absorb one photon at a time. He also made the atomic theory of matter. He published this paper in 1905 in regards to the movement of tiny particles floating in a liquid or gas. It was known as the Brownian movement, found earlier by the scientist Robert Brown. This theory found that even though observable particles are much larger, they generate pressure the same way as the invisible molecules that they are immersed in. Since atoms and molecules flow to even out their concentrations, so do the large particles if their concentration varies. The large particles are immersed in invisible molecules. Einstein's paper confirmed this atomic theory of matter through mathematical calculations and experiments, being the first proof that atoms exist in Brown's time of 1827. With this calculation, one could determine the size of invisible atoms and determine that heat was created with the motion of atoms and molecules.
Drum roll, please. The moment you've all been waiting for, titanium! Let's bring in our science expert, Gabriella. Could you give us some titanium background, please?
Titanium, first discovered in 1791 in Cornwall, England, by clergyman and amateur chemist William Gregor, is a hard, shiny, and strong metal. Titanium is the 9th most abundant element on Earth, most usually found in igneous rocks and their sediments, and is believed to be the 9th most common element in Earth's crust, about 0.6%. It derives its name from the Greek word titanos, with respect to the Titans of Greek mythology. Have you ever taken a trip to the moon recently? I think the answer for most of you is no. So we are here to tell you that if you did, you would find titanium. That's right, titanium can be found on the moon. Fun fact for all you brainiacs out there, titanium does not actually occur in nature as a metal, but is as strong as steel, but a whopping 45% lighter and is 30% more elastic than steel. And for those wanting to travel with their Apple laptops on their next airplane trip, no worries getting through security because titanium's low magnetic signature reduces visibility to metal detectors and can't become magnetized. Feel free to bring any titanium to the beach because it's resistant to salt water, perspiration, and acids, which the latter hopefully won't be found there. Titanium can only be worked with extremely hard tools due to its extremely high melting point of 1,800 degrees Celsius.
And what about the isotopes?
Now on to our good old isotopes. Isotopes are variants of a particular chemical element that have the same atomic number, but different atomic masses. Each isotope had the same number of protons, represented by the atomic number, but different numbers of neutrons due to their different atomic masses. For titanium, there are 5 most common naturally occurring isotopes, being Ti-48, Ti-46, Ti-47, Ti-49, and Ti-50. This relates to the representation of the periodic table as the most common isotope, being Ti-48, with an abundance of 73.72%, is the one that is represented on the table. The other common isotopes are not present for titanium. However, the mass of Ti-48 is representative of all naturally occurring isotopes, as the mass is calculated by first multiplying the mass and natural abundance for each naturally occurring isotope, and then adding all of those values together to achieve the mass found on the periodic table.
Cool! To sum that up, titanium is located with the transition metals on the periodic table. Titanium has an atomic number of 22. That means it has 22 protons and 22 electrons, since atomic number is the same as proton and electron number. It has 2 valence electrons. That means that there are 2 electrons in the outermost shell. It has around 25 neutrons, depending on the isotope. The average atomic mass is 47.864 AMU. Titanium has a melting point of 3,034 degrees Fahrenheit and a boiling point of 5,948 degrees Fahrenheit.
Now that we have some information on titanium, let's find out how titanium can be used in the real world.
Titanium has a lot of uses in modern times because it is as strong as steel and yet very light. It is most commonly known for its excellent strength to weight ratio. The metal resists corrosion at higher temperatures because of the protective oxide coating which forms on it. Titanium is commonly used for airplanes, firearms, and sporting equipment and jewelry. Titanium is personally my favorite element. It is used in most Apple laptops. As Gabriella said earlier, titanium has a low magnetic signature, which reduces its visibility in metal detectors.
Is there any good uses for this fascinating element, and can it help society? I am very interested.
Glad you asked, because there is. Titanium is used for alloys with aluminum, molybdenum, manganese, iron, and other metals. These alloys of titanium are used principally in the aerospace industry for both airframes and engines, where lightweight, strength, and ability to withstand extremes of temperature are important. Titanium is as strong as steel, but much lighter. It is twice as strong as aluminum. It is nearly as resistant to corrosion as platinum. Titanium is a component of joint replacement parts, including hip, ball, and sockets. These may last for 20 years or so. Titanium is used in dental implants because it is able to osseointegrate. This results in implants, while not cheap, can last 30 years. It has excellent resistance to seawater and is used for propeller shafts, rigging, and other. The dioxide is used extensively for paint as it is permanent and has good covering power. Titanium oxide pigment accounts for the largest use of the element. Titanium is truly fascinating, guys. Woohoo!
That's all we have for you today. We hope you enjoyed this episode of Elemental Distress, and we hope to see you next week. Make sure to drop in the comments below the element that you want discussed for next podcast. Now, I'd love to make chemistry jokes, but all the good ones are gone. So here's one we came up with. Florence Flask was preparing to attend the opera. Suddenly, she screamed, "Erlenmeyer, my jewels! Somebody has stolen my jewels!" Her husband replied, "Relax, dear. We'll find a solution."